This is the end of 7-6. We did it in 3 days. These are the application problems. So we can see the first one says a population of 7 spider monkeys live in Post Malone's personal zoo. He plans to triple the spider monkey population in size every 10 years. The function y equals 7 times 3 to the power of x, where x is the number of 10-year periods, models the population growth. How many spider monkeys will Posty have after 20 years? Is this an insane situation? All right, so we see that we have the equation y equals 7 times 3 to the power of x, which makes sense because he's starting with 7 and he's tripling the population, right? So he keeps multiplying by 3. So x is the number of 10-year periods, and we want to figure out how many he's going to have in 20 years. So if we're talking about 20 years, right, 10-year periods, 10, 20, that would be 2 periods, right? 10 years, and then 10 more years would be 20. So we'd have to plug in 2. So we'd have 7 times 3 to the power of 2. Well, we know the exponent first, so that's going to be 7 times 3 squared is 9, which is going to be 63. So there are going to be 63 spider monkeys there in 20 years. Second part, is that an insane situation? I'm going to say that 63 spider monkeys is pretty insane. All right, next, a population of 12 cute little baby sea turtles were found in a random puddle in the middle of nowhere and put into an incredibly large tank. It's predicted by Travis Scott, I put Scoot, that their population will double in size every 10 years. The function y equals 12 times 2 to the power of x, where x is the number of 10-year periods, models the population growth. How many, another typo, how many should be cute little baby sea turtles will there be in 50 years? So again, we have our equation, y equals 12 times 2 to the power of x, which would make sense because the initial amount we're starting with is 12. It's doubling, so that would be you keep multiplying by 2. We want to figure out, let's see, in size every 10 years, so we're talking in 10-year periods, and we want to go 50 years out. So that is going to be x equals 5, right? X would equal 5. So we do y equals 12 times 2 to the 5th, exponents first, right? So we'd have y equals 12 times 2 to the 5th is 32. 12 times 32 is 384 cute little baby sea turtles. That's a lot of sea turtles. Next one, a student promises Mrs. Cole to reduce the amount of garbage that comes out of their mouth by 2% each day. The student currently averages 27 garbage comments each day. The function y equals 27 times 0.98 to the power of x models the average amount of garbage coming out of the student's mouth after x days. Graph the function. When should Mrs. Cole stop nagging the student? I like this. So we've got y equals, starts with 27, which should make sense because that's what they're starting with, times 0.98 to the power of x. Why that is they're reducing by 2% each time, right? So the full amount would be 100%. So if they're taking off 2%, that means they're still keeping 98% of their trash talk comments, right? And 98% as a decimal would be 0.98. So that's where that number came from. So if I want to pick some values here, I could do, so these are representing how many days, right? So at the beginning, 0, we know it's going to be 27 days, right? If we plug in 0. So 1 day out, I'm going to use my calculator. I'd have to do 27 times 0.98 to the power of 1. I'm at 26.46. After 2 days, I plug 2 into my calculator. I'm at 25.9308. Not going down very fast. So I'm going to jump to 10 days. After 10 days, plugging into my calculator, 27 times 0.98 to the power of 10, we are at 22.06. So I'm going to go 20 days out. 20 days out, I'm at 18.02. So I'm definitely going to change what I'm counting by here, right? I'm going to go every other line and count by 5. So 5, 10, 15, 20. I only need the first quadrant because these are all positive. I'll do the same thing over here, 5, 10, 15, 20. So I had 0, 27, 126 point, oh, these are really close together. I'm going to jump out to 10. I was at 22-ish. And then at 20, I was finally at 18-ish. Right? So there is data that can't actually happen over there because we can't have a negative amount of days. So if I want to talk about when am I going to stop nagging the student, probably not until it's close to 0. So this student has a long time to get Mrs. Cole off their back. Next one, a solid waste disposal plant proposes to reduce the amount of let me start over. A solid waste disposal plan proposes to reduce the amount of garbage each person throws out by 5% each year. This year, each person threw out an average of 1,700 pounds of garbage. The function y equals 1,700 times 0.95 to the power of x models the average amount of garbage each person will throw out each year after x years. Graph the function, right? So we've got y equals, it makes sense, 1,700 is what you're starting with, times 0.95 to the power of x, right? Because they're going down by 5%. So a full percent is 100, so minus 5 would be 95%, which is 0.95. All right, so we have amount of days here, so I'm just going to pick some numbers. I'm going to go 5 days, 10 days, 15 days, and 20 days. I'm saying days, but it's actually years, isn't it? Each year. So we're going to do 5 years, 10 years, 15 years, 20 years. So when I plug in 5, 1,700 times 0.95 to the power of 5 is 1,315. 10 gives me 1,018. 15 gives me 788. And 20 gave me 609. So obviously, again, I'm not going to count by ones. I only need the first quadrant. I'm going to count by 5,000. So every other line, so we've got 5,000, 10,000, 15,000, 20,000. I'm going to go every other line and count by 5. So 5, 10, 15, 20. So 5 years, I'm at 1,300. Whoa, I picked way too big. What if I take those down? 500, 1,000, yeah. Oh, no, we're good. This one, I am wrong. This should be 500. Here, let me read. I picked too big of an interval. So let's do 500, 1,000, 1,500, 2,000. That makes a lot more sense. So then at 5, I'm at 1,315. 10, I'm a little over 1,000. 15, I'm at 788. And then 20, I'm at 609. So we can see this exponentially decreasing towards 0. So those are some examples of some word problems.